So, yeah, I will, during this talk, use NaxRiscv to talk about the pipelining API and the plugin API it implements, and dive a bit into the Scala and SpinalHDL interaction. So, NaxRiscv, it is a core I started developing October 2021, which is a RISC-V, 32-bit and 64-bit core. It has everything you need to run Linux and Debian. So the FPU, compressed instruction set, supervisor, MMU, and atomic. It is out-of-order core and superscalar core, so it can also run multiple instructions at the same time. Free open source on GitHub. And one reason of this development was to experiment even more than NaxRiscv into how to elaborate the hardware. One thing you know, it is this core targets FPGA with distributed RAM, so it will infer quite well on, for instance, Xilinx FPGA. And yeah, for instance, here there is somebody which used it to run Doom in a reverse engineered oscilloscope, and it ran really quite with some decent performance. So it's really not the subject of this talk, but just for reference, it's about double what you get with a normal in-order soft core, single issue soft core. Frequency is not that far off what you will also get with a normal in-order soft core. Area usage is obviously quite a bit bigger. I would have hoped to have something a bit smaller, but considering it is an out-of-the core, it's not that bad. Especially if you look out there in the open source scope, there is really not that many out of the core, and it compares quite well. The architecture, so yeah, I will not dive much into it. It's just for reference. Like in general, the core is configured with 2 decoders working in parallel, 3 execution units, 2 general purpose GLU, and 1 shared execution unit for everything special, like load, store, multiply, divide, and so on. The core does register renaming, generally configured with 64 physical register. It has some branch prediction, not the best in the world, but something which fits well in FPGA. Does the job. And to give some idea, if you have a misprediction, you lose 10 cycles. So the data pass for a mispredicted branch is quite painful. And the data cache is non-blocking, so the core can do multiple line refill and line write back at the same time. And so based on all of this, the main topics of this talk will be pipelining API, and the way the top level is composed of multiple things. It's not a regular top level where you have all the modules instantiated and connected together. It's quite different. And so for the pipelining API, I will do it via live coding demo. This way, it's a bit more to see the flow, how things could be made. And so here I go. I have here, no, this. Okay, this is a little template I have where we run a simulation, we capture the wave, we want to compile a top level, which is a component with 3 inputs, X, Y, Z, input unsigned, and a result output. And the processing we will want to do in a pipeline manner is X times Y plus Z with using the pipeline API. And here what I have is just a little test bench with put everything to 0 at the beginning, and we'll place some value 2 cycles later, and then put everything back to 0. Just a simple test bench to demonstrate. So you could pipeline this by hand. Pipelining by hand is very fine for cases, for many cases, but for a CPU design where you have many parallel parts in the design which have to integrate themselves on the pipeline, have a bit ratio, it can really become tedious. So as a demonstration, I will use the SpinalHDL pipelining API. So import spinal.lib.pipeline here. Define a pipeline being a new pipeline. Yeah. And then, for instance, in it, I can define 3 stages, A, B, C. And then, for instance, I want to connect those stages together. So I can do, okay, connect A to B and connect them in a way which is add a register stage from A to B. I will do, for instance, the same from B to C. So this means I register stage from A to B, I register stage from B to C. And then, for instance, here I can define signal or things, hardware things which go through the pipeline. I can define, for instance, X, Y, Z. This time in uppercase, why not? Which are stageable of the uint 8 bits hardware type. And stageable, so it's not a signal, it's like a hard type. So in SpinalHDL, you have a concept of hard type, like your hardware type, you can define it like this. And you can give a given type like sint of 8 bits. And if you want to create a signal of this type, you can say, okay, my type craft. You can craft this type. You can add it to the netlist. You can instantiate it in the netlist, or directly my type bracket works too. So a stageable is a hard type which will be used as a key to retrieve some signal across the pipeline. And so you can say, okay, in A, I want to specify that the value, the things that is represented by X uppercase is assigned with my input X. Can do the same for Z and Y. And here, so I pushed signal at the first stage of our pipeline. And for instance, if I want to do the multiplication in the stage B, I would say, okay, B of X multiplied by B of Y. And I want to push that result into the pipeline again. So I can define a new stage variable, XY, as a stage variable of uint 16 bits. And okay, stage B, XY, assigned by my value. And finally, for instance, in the stage C, I will retrieve XY, add Z, and assign that to result. So here it's one variation of the syntax. I will come later with other variation of the syntax, which can make things more smooth. So, and then now that I specified everything to the pipeline API, because each time I does that, basically what will happen is that the pipeline and the stage will store this information into some kind of hash map and data structure. And once all those things are specified into the data structure, I can say, okay, build yourself. Build the pipeline to connect all those people together with the proper connection. And so if I run the simulation, oh yeah, I need to rename this. Oh yeah, that's quite bad. Okay, I need to comment that. I was doing some other development in that same project, so I need to comment that out. Good. Okay, the simulation is running. I can check the signals, our input, clock, and reset. Why not? So our stimulus from the test bench are there. And here we can look at what that generated. It generated some kind of nice pipe underscore A, X, Y, Z. So that's what we inserted in the pipeline. And we can retrieve those X, Y, Z in stage B, for instance, delayed by 1 cycle as we specified. And we can retrieve X multiplied by Y there. I mean, that's really to show that how things are named and generated corresponding to our description. So we can retrieve all those things easily like this. And just to check the result, we come, okay, from A to B and B to C to stage latency. And so now that's one way of defining things, but we can do things differently. We can, for instance, move all those stage level definitions on the top. And those stages, we can define them as proper things. Each, like A will be a unused stage. And in stage A, we will do this. We will insert our signals. We don't need to refer to A each time, so we have much less verbosity. Then we can do the same with B and C. And we move that B pipelining there. And the result in stage C. And there we go. That's another way of defining the pipeline. So now it means the connection. So connections could have been done as before, like connect this stage, but we can also specify the connection of stages together in a sequential manner, like saying, okay, stage B will be connected to the previous stage using this connection type. That's another more direct way of specifying things. So if I generate the code, it's good. Okay. And even further, here we define the stageable key separately. But for instance, we don't really need to do that. We can specify, okay, XY being the insertion of that hardware value in the pipeline. And this insert will return the stageable instance to represent that hardware value in the pipeline. And just that now I need to refer to BXY here. So in that way, you can avoid having, like if you are carrying types over and over further in the pipeline with transformation and things, you don't need to each time define what type is XY, because it will take the type from that result. So it can be quite useful if you have long processing pipeline, not have to manage all of this by hand. The same could be done for XYZ here to insert them directly instead of defining a stageable pair. And now I will just demonstrate a few of the tricks and tips of the API. For instance, there is an option of having a sub key. For instance, imagine you have a CPU pipeline when you define a stageable for the program counter as a uint of 32 bits. At a given point of the pipeline, you may have multiple variations of this program counter. For instance, in NaxRiscv, you have multiple decoders working in parallel in the same pipeline. So you have program counter for the first decoder and program counter for the second decoder. And one way to handle that is, for instance, to say, okay, I have PC with a secondary key for decoder 0. It will be secondary key will be number 0, and can create like this new keys composed of a primary key and a secondary key. Another example is, for instance, maybe in your branch prediction, you need to have two variations of the program counter, of the next program counter, like if the condition is true or if the condition is false. So when you generate these kind of things, here you will retrieve in A, PC0, PC1, PC false, PC3, true, and all these kind of things. Another thing with this API is that you can manage arbitration too. You can say, okay, when, for instance, XY is smaller than 100, and say, okay, I want to halt the pipeline. I want to block the pipeline there. So there is multiple utilities to manage arbitration. Like you can remove the current transaction of the pipeline, or you can flush all the transaction in the pipeline from the current stage and above, or you can flush all the transactions in the pipeline which are above stage B. So this is the kind of things you can do. Here, just to have it working, I will just make an assumption that in stage A, the insert that we have a transaction each cycle. And here, if we generate this hardware now, and we will check in the generated hardware, we will find that in stage B, we have a halt request, which corresponds to this halt here. Okay, so stage B, halt request from the file demo, line 573. So we have this kind of backtrace which are done, and now I will just show a few tricks how to preserve name in SpinalHDL, how to define API to provide this kind of nice naming schemes. And so there is multiple ways. Like, okay, imagine you have a function, like let's say halt it, but let's name it func. And this function need to define something internally, like let's say bool. You can provide a name to this meow by many ways. You can, for instance, say, okay, meow.setName. Like, it will have this name in the netlist then. But you have more ways, like you can set composite name, like take the name of the stage B and add this postfix. I need to call the function at least once. And here we have pipe B, woof. There is other ways, like one recently added was set lambda name. With lambda name, you have to provide two parameters which say if you are able to provide a name, like let's say we want to compose a name with stage A and stage B. So stage A need to have a name, and stage B need to have a name. And then you provide a lambda function to provide a final name. Like we can say, okay, maybe we start with this, then we compose a name with a.getName, and then let's say b.getName, and let's call bbb. And here we will have our signal composed with a complex name. So the thing to remember is that if at that moment here, if I ask the name of the stage A, SpinalHDL will not be able to provide us the name at that precise moment because A is in the pipeline pipe, but pipeline pipe is not yet named. So that's the reason why here set lambda name work with lambda function to delay the processing of the name. Like here we can see I just run that code and it's saying name is, no name yet. So and another thing was the location. Like if you want to provide to know at which line a given function is named, it's a bit like in C, you can have some kind of macros to do that. You can say implicit loc as location. This is a spinal epistomal, maybe. No, well, I don't remember from which has to be imported, but it's from the SpinalHDL library. You can say here loc dot. It's not finding it. I don't remember why. We just skip a bit. Yeah, it's finding it there. I don't know. I will not waste too much time on it, but basically, you can use these kind of tricks, which will give you the line and the file name at which this function func was called. I think I'm just trying now to think if that's everything I wanted to show about this pipelining API. I think it is. Yeah, I think it is. And so, one thing that this kind of pipelining API allows is like you can have functions that will add hardware on the pipeline in a very composable way. Like for instance, you can have a function which will do some floating point add, which will work over multiple stages. You will have to specify on which stage you want to do this floating point multiplication or addition with which input values, and you can call this function multiple times over the same pipeline. As long as you use different stageable key, you can compose a pipeline in that manner. And NaxRiscv use this kind of things quite a lot. And so now come a bit the second part of the demo, which is SpinalHDL support multi-threaded elaboration, not really in order to improve performances, because that will not improve performances, elaboration speed, but as a way to be more expressive. So second demo is, and then I will come back to slides. Second demo is about negotiating, for instance, ports to order the CPU to do branches. So, okay, let's define a simple thing where we will generate some Verilog of a new component. And let's say, okay, we want to define a CPU which has to manage a program counter, and there will be multiple pieces of hardware which need to ask a jump port. So jump ports could be an array buffer, so it's a mutable list in Scala of flow uint, flow uint. And for instance, we will have somewhere a PC, which is a register of uint 32 bits. And to manage all those jump ports here, we can use, a simple for loop, let's say port. And when the port is valid, then, my PC, I can assign it with the value of the jump port. And let's say here, we just print that to say, elaboration found, we have a jump port. And for instance, here, if I have my branch prediction, for instance, I need a jump port for my own usage. I can say, predictor jump is flow uint 32 bits. I need to add this jump port into the list of jump ports. And if I generate this, this. Okay, we got a jump port. Now, the complexity comes when you have multiple hardware which may need a jump port you don't really know yet, and maybe they need something else, and maybe this hardware here needs other resources from other pieces of the hardware. So if you have a really well-defined problem, you may be able easily to define, first I need to define the list of ports, then I add all the ports I need to it, and then I use this list to do something. So if you have if you have not too complicated cases, you can do that by hand, ordering which order you do things in your elaboration. But when things get wide and very flexible, a bit less. And so to solve this, one approach is to define thread. So let's imagine that, we have an elaboration thread, like predictor thread, which is a hard fork. So it will fork an elaboration thread. So to have this hard fork, you need to import spinal.core.fiber. So, here we can define one thread which will do that, and another thread which will do that, PC thread, to do the elaboration of this hardware. So I could now run my elaboration. It will still work. It still got one port, But the question now is, okay, what's if I change order of things? It will not work anymore because depending the order in which threads will be executed, we may execute this first before adding our port. So we can define lock and mutex like jump ports lock, which is a lock. And for instance, our PC thread will, before elaborating itself, wait on that lock. Await. And for instance, here we can retain that lock. So locks in SpinalHDL works really like a counter. You can increment it by retaining it, decrement it by releasing it. You can release a lock. And in that way, you can describe your hardware description in a multi-threaded manner as a way to be more expressive and to decouple the elaboration phase of your hardware. And that's really how NaxRiscv is made. So if I think I can go back to the slide. So VexRiscv has kind of something a bit similar, but it was not using independent thread. It was really using callbacks to generate itself. But NaxRiscv goes one step further and really has elaboration thread for every little part of the hardware. And so, okay. So here you can see how to create an instance of NaxRiscv. You insert it, you give a list of plugins. If you look at the top level of NaxRiscv, it does not define any hardware. It's like 2 lines of code and it does not generate any hardware. It just handles plugins. Okay, and a list of plugins. Okay, it is array buffer of plugin in which, for instance, you will have one plugin to manage the program counter, a bit like you have seen before, one plugin to manage the fetch instruction cache, to decode, one to dispatch, one to commit instructions. There will be one for the MMU, one for a bit everything. And for instance, if you want to add an execution unit, let's name it ALU0. You can come in the list of plugins. You can say, okay, I want one execution unit base, which is kind of a skeleton of execution unit. And then you can add other plugins which will compose that execution unit with their behavior, like one plugin to implement the int ELU, one to manage the shift, one to manage the branch, and so on. And for instance, if you want to add a second execution unit, you come and I'm completely lost now. Yeah, you come and you just add another set of plugins with a different you add another set of plugins to which will work on another execution unit base, and you can really compose your CPU top level in that way. And so, as a demonstration of how it works, I will show you, for instance, how you can implement a custom instruction plugin, which will do a single instruction multiple data add. So, a plugin in NaxRiscv is, okay, it's a class. In this specific case, we will work with a specific execution unit. So have this parameter, Texan the base class plugin. And this base class plugin allows us to fork elaboration thread in an orderly manner. There is two order. You can create an early thread, create early threads, which will generate a new area. And this early threads are used for plugins to negotiate things between each other and to notify each other of things, or to retain each other's of doing things because it's too early. And then when everything is negotiated, you can create a late elaboration thread that will be used to generate all the corresponding logic of your hardware and everything you need to really implement the behavior. And so in our case, first, for instance, our custom instruction will need to retrieve the execution unit skeleton on which it is working on. And for this, it can say, okay, find service of this type, which is working on the same execution unit ID than us. So that way, it will retrieve the plugin which implements the pipeline for this execution unit skeleton. And first thing this plugin will do is say, okay, I will specify to you a few things later on. So execution unit, you should not elaborate yourself yet. I have more things to tell you. And then, for instance, okay, we can define the encoding of our instruction as a RISC-V type R instruction encoding with this bit mask. And then we will delegate to the execution unit a few things to manage. Like we will specify to the execution unit that the add8 encoding is supported inside its pipeline. And this will have a few cascading effects. The execution unit will then notify the dispatcher that add8 instruction could be dispatched to itself. And maybe the dispatcher will notify some other piece of the elaboration about some requirements. Another thing is, for instance, we specify to the execution unit that the add8 instruction will execute with a fixed latency. And when it reaches stage ID 0 of the execution pipeline, the reorder buffer can be notified for completion. And instruction which depend on us can be statically waked. And for instance, here we are mixing a bit of the pipelining API. So we are composing the pipelining API. Like we are defining cell as a stageable key of the Boolean type, and cell will be used by our plugin to specify if a given instruction in the pipeline is an add8 instruction or not. And so here we define a stageable value, and we will delegate to the execution unit base the responsibility to decode the instruction to the cell signal. Like we specify, by default, cell has to be false, but if you decode an add8 instruction, please set cell to true. So plugins can negotiate things between themselves in this kind of way. And when all of these kind of things are done, we can move to the elaboration phase where we will really generate the hardware related to our functionality. Like, for instance, here, the execution units have always like 2 fetch stages to retrieve the context of the instruction, and then 1 or more execute stages. And here we ask the execution unit to provide us elaboration time reference of the execute stage 0. And this will give us a stage from the pipelining API. And on that stage, for instance, we can retrieve register source 1 and register source 2. And then we can do our regular SpinalHDL hardware. We do our processing. And once we did everything, then at the end, we release the execution unit lock. We tell the execution unit that we have nothing more to ask it. It can generate itself safely. It has all the information now. And yeah, that's how the NaxRiscv elaboration is done. Then, yeah, for instance, you want to add your custom instruction to the CPU. You just add 2 of those, 1 for ELU0, 1 for ELU1, and things will work out. And that way, we compose the top level of the CPU in a really composable manner. And what I mean is that we didn't modify any line of code. We created new line of code. We didn't have to plunge into a top level and bind things in a painful way. And yeah, that's it. So project status of NaxRiscv is, there is also the GTAG support to debug it. This time it's official RISC-V debug specification. Planned for the core is multi-core and memory currency. Got Debian to run. So yeah, next step is multi-core and memory currency. You can find it on GitHub. If you want to deploy it on hardware, currently it is on Litex. And yeah, I have to say thanks to NLNet for the funding to implement this project. So yeah, that's it for me. So yeah, I'm open for question if there is any. Okay, so chat. Yeah. Just trying to find the first one. So the question is, are stageable just mean that it can be used as element within the stage to do logic? Yeah, stageable is more like saying it's really a key to retrieve a concept in the pipeline. Like the program counter along the pipeline could be retrieved using a key, and that key will be the stageable thing. It's really like an identifier which will be used in a hash map to retrieve the hardware signal. So you can use that key in a specific state to retrieve that signal. And then the pipeline will link all those things together. Like, yeah, the stageable itself will not create logic. You will create logic with the regular SpinalHDL API. So is the pipeline lib described in the document? To be honest, I'm really not sure it is. Maybe I think it is. I think I did it a bit. I think it is. Yeah, let's check that fast, but I think it should be in library. Or maybe I think I documented it, or maybe it's in the NaxRiscv documentation. I think in one of both it has to be. Yeah, it is. It is in the it is there. It is in the NaxRiscv reader documentation. Not fully. Has to be better. Okay, could this API be used as a basic for the plugin system in NaxRiscv, or other approach orthogonal? So NaxRiscv is implemented in a okay, yeah, I answered it already, but yeah, NaxRiscv is implemented using callbacks, one early callback, one late callback. So one negotiation callback, one delayed callback. That work in most cases, but in some time you have dependencies which are longer than 2, and that become really an issue then. And NaxRiscv really solved it in a better way. And okay, well, also one funny thing, for instance, if you look, one plugin is the fetch plugin. And the fetch plugin is just implementing a pipeline skeleton for everything which is about fetching instructions. I will just have to say until when I have, okay, I have 7 minutes more. Okay, so that plugin basically implement a pipeline that others can use and compose. So you like in NaxRiscv, NaxRiscv was a pipeline on which plugins will compose. But now pipelines can be plugins. So you have plugins providing pipelines for other plugin to compose on. So it's kind of one step further. And the funny thing is, like, this fetch plugin do not define the length of the pipeline, so that the plugin working on that the plugin using the fetch pipeline, which can specify how long they need the pipeline to be. Okay, so currently, the RISC-V specification, okay, a few things about the debug spec. So I recently implemented the official RISC-V debug specification in VEX RISC-V. It was a port from Nax to VEX. So yeah, just thanks. So I have to say thanks to FNX for the funding. And so it is a version 0.13. So version 0.13, I think, is kind of close to the RISC-V debug specification 1. So version 1 of the RISC-V debug specification is kind of close from the 0.13. So I guess it may. I would have to check what are the exact changes, but it should not be much. Debug spec version 0.11 was really, really different. Is the question if there is a plan to follow the evolution of the debug specification? Like, I would say not really, unless there is a need. So if there is really a need, it could be followed. I would say it's probably not a big deal at all. Also, one thing, like all the debug of this kind of feature can be done in simulation, so it's really easy to debug this kind of debug feature. The V extension support, there is no plan for it. Yeah, there is really no plan for it yet. It could be interesting, but it's also quite complex, especially with the memory system of the vector extension, I would say. But I don't know so much about it. So to me, it's something which afraid me a bit. So currently, I really have no plan for it. So question is, for the pipeline API, is there a way to generate register row or not based on parameter? May need it or not, depending the target Fmax technology. So I'm not sure exactly what you mean by a register row. Do you mean having a longer pipeline, or you mean? I'm not sure to understand it.
Yeah, I mean, sometimes you need to have one row of register to achieve one given target frequency, and sometimes you can just do everything in a combinational way.
Okay. So you mean a longer pipeline?
Yes.
Okay. I can show a little bit. For instance, I have the data cache plugin, and here, for instance, the parameters is like, okay, like read the banks of the memory at stage 0, read the tags at stage 1, do the hits at stage 1, do the aggregation of the hit at stage 1, and do the control at stage 2. And basically here, the idea is that you can specify at which stage you want to do things by a number. And then when you implement the hardware, you say, okay, take the stage ID this to provide us a stage, and implement then the logic, like control stage, then implement all this logic in that stage. So in some ways, yes, you can do these kind of things via parameters. It needs a little bit in the elaboration by hand too, like defining the stages, indexing them. But it's one goal of the pipeline API is to make longer pipeline much easier to implement. It's not retiming, it's still manual, but it helped already quite a lot. So I just have 1 minute left, so I have to be fast. So can you add the demo so it's easy to try it and change what you showed us? Yeah, sure. I can commit them. Sure. So yeah, that's it for me. I think now we start the next talk, which will be from Sweden. So I will stop the screen sharing so he can take the hand.